Z and X view, right? So this is the feature that we want to machine. Okay. So this is our tool, right? When the tool is going clockwise rotation. So in the next cut, what you see over here is you see this, right? So the tool will do an engagement down here. So the left side, okay, so this is what we call left, and this is what we call right. On the left side is up milling. On the right side is down milling. Okay. So in any operation, the first cut that you want to reach a certain depth is usually slotting, and this is no good. Okay, for high B and N number, this is no good. So what we tend to do is we tend to modify the cutter path. Okay, so this one, the tool just go in this way. Okay, so what we tend to do, and I've tried myself in a company before, we were making landing gears for the F-18 jets, and this is in 2010, 2011. Okay, so one of the planes had a heavy landing on an aircraft carrier. Okay, so it's known as trochoidal cutter path.
Hey Eugene, question. Instead of changing the path of rotation, couldn't you just change the direction that the tool's rotating?
No, you can't.
Why not?
Because the tool only can cut in a clockwise direction. If you are going to cut in an anti-clockwise direction, you have to use a different tool.
Oh, okay, so there's no like bi-directional tool.
Yeah, no.
Okay.
Only even drilling is no bi-directional.
Okay.
So the only way to do this, you guys can Google this, okay? Trochoidal is you use a smaller tool, okay, and you do this. This is your cutter path. Down milling. Okay. So this is the best way to open a slot, okay? Okay, best method to slot material with high B and N. Okay. As I said, I was in a company known as Heru DevTech, okay, in Cambridge. They make the landing gears for the F-18, okay, and we have to produce a landing gear once called upon, delivered within 48 hours. Out in the Middle East, can be anywhere, okay. So when we produce landing gears with high strain hardening sensitive, this is the only way to open the slot. And as I said, done it before, okay, physically, okay, and it's the only way, okay. If you try doing slotting, no way that you can there's no way that you can cut the material with high B&N. Okay. Now I'm not going to talk about strain rate sensitivity, okay, because you all know if material we have high strain rate sensitivity, the higher speed you cut, higher stresses. But rather, I want to look at the thermal softening index. Okay. So the thermal softening index, the formula is 1 minus theta ambient over theta melt minus theta ambient of M, right? So the thermal softening index okay, the thermal softening index can be used if increasing the cutting speed will benefit in reducing the stresses acting in the tool. Okay, so I'll give you an example. If we have M, okay, so one M is 0.5, the other one M is 1.5. Okay, so if we were to over here is if we were to increase cutting speed, right? The 0.5 will have what? Benefit. The M is at 1.5 will not have any benefit at all. So as you all can remember, right? So I'm going to draw this graph for you guys again. You guys will say, oh yeah, I remember that. And over here is 1 minus theta ambient over theta mel minus theta ambient, right? And this is 1, right? This is M is equal to 1. M is greater than 1. M is less than 1. So if M is less than 1, right, this is 1.0, right? Let's say if we operate at this temperature over here, right? Right, if we operate at this theta over here, the M is less than 1, it will reduce by maybe it will reduce to 0.2, for example, or 0.3, right? So increasing the speed does help, okay? Over here, when M is 1, increasing the speed only drop by 0.9. However, when you increase the speed, strain rate increases, right? So when strain rate increases, this might not benefit. So for high strain rate sensitive material or for high value of M like 0.5, you can increase speed. If M is at 1.5, you cannot increase speed. So this is how we judge by looking at the thermal softening index to see whether will it be beneficial or not. Okay. So the softening index can more or less tell you if you increase the speed, what will happen. Okay, you don't need to do an experiment for this. You don't need to pay institute to do. You just look at the M number. Okay. So from here, I just showed you how to use mechanical properties to anticipate what's going to happen when you cut or do optimization. Next, we are going to look into the mechanics of metal cutting. Okay, we are going to look into mechanics of metal cutting. So we are going to draw what we know as merchant circle. Okay, and merchant circle has nothing to do with Mohs circle. I repeat again, merchant circle has nothing to do with Mohs circle. Okay, so you first have to construct a circle. And this is the center of the circle. And then we are going to put the two rake face. So the two touch one part of the circle. Okay. So that is our alpha, right? So alpha corresponds to our rake angle, as you know. Okay. So this force over here, this line will draw within the circle. This is known as our FC. Okay. So FC is the force acting parallel to the rake face. Okay. Then I'm going to draw a line down here. This is known as R. I'll draw R down. R is known as our resultant. Okay, cutting force. Okay. And then from here, we know based on the rules of the circle, remember? This will be our NC. Okay. So NC over here correspond to the force acting perpendicular to the rake face. Okay, so for now, I will request that we go for a 15 minutes break, and then we come back again, we continue. Okay.